The purpose of this module is to explain gas exchange and then how those gases, oxygen and carbon dioxide, are carried in the blood to and from tissues. The objective of this module again are to compare gas exchange in the alveoli to that in the tissue and discuss how oxygen and carbon dioxide are transported in the blood. We will also describe various respiratory diseases and their causes. Air is present throughout the respiratory system from nose to alveoli, but only in the alveoli does gas exchange take place. Some of the air you breathe in remains in the nose, the trachea, and the bronchi, etc., and doesn't get all the way to the alveoli. And no exchange of gases can take place in these locations, so it is considered anatomic dead space. So again, anatomic dead space, places where air is, the gas exchange cannot take place. Alveolar dead space occurs when the blood flow stops. Gas exchange, remember, is by diffusion, so it goes from high to low concentration. And if there's no blood flow movement, then eventually the concentration is at equilibrium across the alveoli and in the capillary. If that's reached, if you get to equilibrium because the blood's not moving, then no gas exchange is going to take place, and it's considered alveolar dead space. If you actually wanted to calculate how much of the air you breathe in gets to the alveoli, you have to subtract the anatomic dead space. This is roughly about 150 milliliters of the air of the 500 mils that you inhale, leaving you with about 400 or 350 milliliters of air for each breath, and about 4.2 liters each minute if you're breathing 12 times a minute. The alveoli have no mucus. This makes it easier for gas exchange. If crud, debris, microbes, etc. get that far, you have to rely on your local white blood cells to phagocytose them. These air sacs have only the membrane of the simple squamous epithelial cells between them and your capillaries. Remember that oxygen and carbon dioxide are small. They're nonpolar. They can easily pass through membranes by diffusion. There's no energy, there's no transporters that are needed, so there's nothing there to break. Movement is always from high to low concentration, and as long as you're breathing and your blood is moving, the concentration gradients are always going to be from high to low. More oxygen in the alveoli because you just sucked a bunch in, and less in the blood. And more CO2 in the blood and less in the alveoli as you exhale. Partial pressure can be thought of as concentration if it's easier for you to think of it that way. Oxygen, again, is at higher concentration in the alveoli after you take a breath in than it is in the capillaries. The opposite is true of carbon dioxide. This picture shows you that. While you don't have to worry about the actual numbers here, notice oxygen is at a higher concentration in the alveoli than it is in the capillary around it. Net movement, therefore, is into the blood, the red arrows here. At the cell, the oxygen is higher in the blood and lower in the cell, so movement is into the cells. Oxygen is used up there as metabolism takes place, and this creates carbon dioxide. It's higher in the cell than it is in the blood, so it diffuses out. And when it gets back to the lungs, the concentration gradient makes it diffuse into the alveoli, so you can exhale it. Oxygen does not dissolve very well in the blood, so it's carried by a molecule called hemoglobin, which of course is inside the red blood cells. Remember, the function of a red blood cell is to carry oxygen. The bond between hemoglobin and oxygen is fairly weak. Oxygen unloads easily at the tissues. In fact, heat, acid pH, and high carbon dioxide levels increase the release of oxygen from hemoglobin. So tissues that are more active, that are warm, acidic, or have high CO2 levels are going to get more oxygen, which makes sense if you think about this, because exercising muscle is going to be warm, more likely to have an acid pH if lactic acid is building up, and high CO2 from metabolism. So exercising muscle is going to get the most oxygen. Carrying carbon dioxide is a lot more involved than carrying oxygen. Carbon dioxide, first of all, is carried 3 different ways rather than just one, like oxygen is. Hemoglobin can carry carbon dioxide as well as oxygen. As oxygen is dumped off at the tissues, carbon dioxide is picked up. But hemoglobin, again, can carry both of them at the same time. Hemoglobin that is bound to carbon dioxide is sometimes referred to as carbaminohemoglobin, which is kind of a weird word to say. Second, a little bit of the carbon dioxide is carried around as a free gas, just dissolved in the blood. But these two together only account for less than a third of the carbon dioxide carried in the blood. Most of it is carried in a pathway called the bicarbonate pathway. This is a chemical reaction that takes place inside the red blood cells, which I will show you on the next slide. But essentially it forms bicarbonate, which acts as a buffer in our blood as it's exchanged across the membrane of the red blood cell. So let's look at this equation in more detail. The equation is across the middle of the slide here. As carbon dioxide diffuses into the blood, it mixes with the water inside the red blood cell, and an enzyme called carbonic anhydrase converts it to H2CO3, also known as carbonic acid. So this is water, this is carbon dioxide, this is carbonic acid. This reaction, the red arrow, must occur inside the red blood cell because that's where the carbonic anhydrase is. Carbonic acid dissociates because it's a weak acid into the hydrogen ion and bicarbonate. So H plus is the hydrogen ion and HCO3 negative is the bicarbonate. We're still inside the red blood cell. However, hydrogen ion tends to stay in the red blood cell because hemoglobin is negatively charged and this little dude is positively charged. Bicarbonate, however, diffuses out of the red blood cell and into the blood. Because it's negatively charged, if a negative goes out, a negative has to come in, and chloride comes in as an exchange to balance the charges. And I'll show you that again on the next slide. But the red arrow reaction is occurring at the tissue level because the tissues are making CO2 and water as byproducts of metabolism, and it pushes a reaction like this. But then the blood moves and it starts to go back to the lungs. And when it gets back to the lungs, because you're exhaling CO2 and water, since these are leaving, it pulls the reaction the other way. Bicarbonate goes back into the red blood cell, chloride going out, binds with the H plus ion, the hydrogen ion, forming carbonic acid. The enzyme does the reverse reaction and converts it into carbon dioxide and water, and these diffuse into the alveoli and are exhaled. Okay, so the reaction this way in the tissues, back to the left in the lung capillaries, balancing all the time. Now if hydrogen ion builds up because you're making acid for whatever reason, okay, maybe lactic acid because you're doing a lot of exercise and not breathing fast enough, it's going to push the reaction this way. And breathing rate, remember, goes up to get rid of acid because the hydrogen ion here, indicator of an acid, or is acid, ends up being the hydrogen in the water. And so when we breathe out some of that water, we're actually getting rid of acid, which is very important to maintain pH, because if pH drops, like in acidic conditions, proteins will denature, and that will kill us as they stop working. If you want some more information on the bicarbonate pathway, and you probably do, click on this link and watch the YouTube video. Here's another carbon dioxide transport picture. Again, 70% of carbon dioxide is converted to carbonic acid by the enzyme carbonic anhydrase inside the red blood cell. This disassociates, the hydrogen ion tends to stay in the red blood cell binding to the hemoglobin, and the bicarbonate goes out. Again, because bicarbonate is negatively charged, a negative has got to go in. This is referred to as the chloride shift. It is simply there to balance the charges across the red blood cell membrane. If metabolic acidosis is the first thing to increase breathing rate, why is it that a nurse will measure your blood oxygen levels very quickly in the emergency room? He or she's going to hook up that little blood oxygen thing to your finger quicker than anything else, and yet acidosis is more serious. Okay? One of the reasons is arterial blood is required to measure blood gases. To measure CO2 is a lot more difficult than to measure oxygen levels. Okay, you have to do arterial blood draw, then you have to have the lab work done before you would know that. So generally it's done just because it's very fast and easy to do, and if you're low in oxygen, they can give you oxygen right away. Alright, a couple diseases before we finish this module. Compliance of the lung is how well they expand and recoil. This depends a lot on the flexibility of the lungs and the chest wall. And as you age, this can go down because things just don't work as well. You get less flexible all over. Resistance is how much force it takes to inflate or deflate them. So how much do your muscles need to work? And if your muscles become weaker, it is harder for you to do this. So compliance and resistance can go down as you age. Asthma is triggered by irritants in the passageways and can result in 3 different problems. In fact, there are 3 reasons for asthma. Number 1, constriction of the bronchial tubes. It's harder to get air in and out if the tubes are smaller. Inflammation of the tubes, again, making the tubes smaller. Inflammation can be a result of an irritant or perhaps an allergic reaction. The 3rd reason is increased mucus production. Again, it could be because of an allergic reaction or you just naturally make too much mucus. The problem is ventilation, and resistance is increased because everything's constricted, so it's harder for you to expand your lung tubes. Chronic bronchitis is inflammation and swelling of the bronchi. It can sometimes also be caused by increased mucus, and you cough a lot to get rid of it. The main cause of chronic bronchitis is smoking or exposure, long-term exposure to lung irritants. The problem again is ventilation. Emphysema is destruction of the alveoli, usually because of smoking or disease. The problem is respiration. You can't do gas exchange if your alveoli aren't there. The person can get very tired because the respiratory muscles are working so hard to increase your breathing rate to adjust for this. They tend to be very thin, people who have emphysema. COPD, or chronic obstructive pulmonary disease, is kind of a catch-all phrase for any lung disease which makes it difficult to breathe. There are 2 types. The first type is chronic bronchitis, which brings about long-term coughing with mucus. The second is emphysema, which systematically or systemically deteriorates the lungs. Generally, people diagnosed with COPD have a combination of both conditions. There are no real cures, but there are treatments. Particularly stopping smoking is beneficial, as is exercising, avoiding really cold air, and helping to manage emotions and stress. There are inhalers and a variety of drugs used to reduce inflammation and open the airways. As you age, some emphysema is normal. Obviously, as you get older, all tissues are going to repair less quickly. Lung cancer is quite deadly because it is often detected quite late, and so smoking will increase not only emphysema but your chances of lung cancer as well. Farmer's lung or coal miner's lung, and there's other names for them, bathroom tile layer's lung, for example, is when you're breathing in small particles, dust, mold, etc. After years and years and years, it can lead to lung problems. Pneumonia is a respiratory problem because the alveoli fill with fluid. It's otherwise known as drowning. Pneumonia can be viral, bacterial, or fungal, and sometimes induced by fluid in the lungs even without the pathogens. Hypoxia is lack of oxygen in tissues. Don't get that confused with hypoxemia, which is a lack of oxygen in the blood. Don't forget, you have lots of resources for this. There's a couple of good websites here, as well as lab.